Is Simone Dell'Agnello? It's Doug Curry. Couldn't see you in the glare. You're still giving this talk, right? Okay, international private-public multi-mission payload agreements for next-generation lunar laser retroreflectors. All right, thank you.
Simone couldn't make it, and at the last minute I was asked if I could do something similar, and so I will try and cover that. Simone and I are collaborating on putting together a package, and this work was supported to large part by our recent Lunar Science Institute support with Jack and the lunar package. Okay, the Lunar Science, currently the retroreflectors are on the surface of the moon. It's our only experiment that continues from Apollo days. We've had 45 years of data. And what we do is we measure the distance as a function of time. And from that time series, we can extract physics. For the lunar physics, 15 years ago, we discovered the liquid core of the moon and its parameters. And in the last couple years, Renee Weber has confirmed using seismometry that our numbers were quite good. In general, we can look at the deep properties of the moon, and we've been collaborating with Grail in order to get a surface to core description. In addition, such things as the elasticity, the Love numbers, dissipation of deep regions. On the other hand, a little closer to my heart, we have done most of the best tests of general relativity. In particular, if we project what we measured for the change of big G to the Big Bang, we have verified that the big G does not change to less than 0.5%. For the weak equivalence principle, in addition to verifying what Galileo would have done with lead and wood, what we've found is that we can measure Einstein's prediction that gravitational energy itself is hard to push, that it's got inertial properties. Finally, almost everything people talk about for testing general relativity has to do with static behavior. On the other hand, rotational properties, for example, rotation of the Earth, which is gravity probe B, or motion around the sun and the orbit of the moon, we've been able to get a very high verification of Einstein's predictions for gravitomagnetism. So what we're trying to do on this is to find out to what degree can the explanations of the theories of dark matter, dark energy, be described by variations in gravity or variations in or existence of particles. On the other hand, the package that's up there now has a little bit of a problem. The package is a set of 300 corner reflectors set in this. Unfortunately or fortunately, the moon librates. That means we don't know whether the photon came from the far corner or the near corner. And so what we have to do is to look toward a next generation retroreflector, or NGR, that is a single corner reflector, must be bigger, and provide about the same signal as Apollo 15, which people can range to, the various stations, and gives a good signal through an entire lunation. That's required an extensive set of programs. In particular, the problem is that shortly after lunar dawn, the housing is about 300 degrees Kelvin. The corner reflector is about 70 degrees Kelvin. we have to maintain internal gradients to less than a few tenths of a degree. So we've got an extensive set of programs that we've set up. We look at as the sun comes into the corner reflector, different wavelengths get absorbed different places. The sun is hitting the external, and that's what heated it up to 300 degrees. We have radiation exchanges between space and the hot regolith. And all of these are changing as the sun goes overhead during the lunation. The current design looks like this, the corner reflector. We have a housing which supports the corner reflector. The corner reflector itself is essentially the same design that we had for Apollo, just scaled up a little bit. The support is, again, very similar to what has been operational for 40 years on the Apollo arrays. And also, it's the same design as the corner reflector in almost all of the corner reflectors that are currently in space, many thousands. So the technology heritage is very high, as well as the science heritage, because we've got the results. It's then mounted on what we're talking about here is a lander. It's mounted on the lander. And then we do a thermal simulation of this. And this is the optimization we've come out with. It's also been tested a number of times. A earlier version has been tested a number of times at the facility in Frascati, Italy, which is a state-of-the-art facility. It's also been the facility that's been used for Galileo, also for a number of Goddard tests. All right, the question then comes up, what's going to happen for the science in the future? What do we do with the design in order to optimize this future science? And for that, we've been working with Jürgen Müller and Franz Hoffmann at Hanover, and they have a program. Actually, the program is mainly made in order to analyze data, but it also can be used for projection. And so we can look at what the effect of an increased number of ground stations are. It turns out that with the package, I won't go into the details, we hope to get a lot more stations. In other words, some of the satellite ranging stations will be able to do lunar. This is already occurring. The Italian station at Matera is doing now regular lunar ranging, and the Wetzel station in Germany is started some of that. We want to find out what happens when, for example, a satellite station is limited not to be able to operate during Earth Day or Lunar Day, and the degradation. One of the things that I won't go into is we need to look at the surfaces. Almost everybody, when they do a satellite experiment, they're happy if it lasts for a year or a couple of years. We have to maintain good solar reflectivity and emissivity for a long time. And typically, with these kind of practicalities, it looks like the science parameters are going to be increased by about a factor of 50 over by 2030. I'll skip this. What we found is that traditional ideas of corner reflectors that are out there have some problems. Looking toward the future, what we're talking about is mounting on a lander in the immediate future. What we would like to do is to say, instead of asking that the lander land with the right orientation and not land on a slope, that we would like to have something in which we can point back to the Earth with a small CMOS camera and then move to the center of the libration pattern of the Earth, lock down the axes, and have the good pointing no matter what the orientation of the landing was. And so this actually is a simulation done about 5 years ago. It looks like we now may be able to proceed with a little more detail and perhaps even fabrication. The other future direction is the lander is sitting out there between day and night on the moon. The lander will expand and contract. And so we have a motion there of, depending upon the lander and the details, of 1 millimeter to 2 millimeters. In order to get rid of that, if we go down into the regolith by 0.5 meter to 1 meter, essentially for us, our purposes, the temperatures do not change. And so if I go down into the regolith, lock at the bottom, have the corner reflector on the top, it should be able to allow an emplacement that is stable to about 100 microns. We've done tests drilling. There's a group in Pasadena, Honeybee, that with Chris Zachney, that has proceeded to show you can do that drilling, and has a nominal model that could be used on one of the commercial landers. The ultimate limitation at present would be the modeling of the atmosphere. If, for example, around Washington's hot, suburbs are cold, the atmosphere tilts, we don't know how much, and so that produces an error. Erokas Pavlis has done simulations on that, on how to get the numbers out. That provides a correction that's down at the 1 to 2 millimeters. And in order to get the optimal advantage, we would like to push that further with new modeling of the atmosphere. Finally, this is all good stuff, but how do we get to the moon? Well, rides with NASA seem to be a bit in the future. So we've looked toward the commercial sector, and particularly the competitors for the Google Lunar X Prize. We're working with Moon Express Corporation. Last year in Frascati, we signed an agreement, the University of Maryland and INFN, to fly 4 missions. The first mission is expected to occur late in next year, 2017. And so, in conclusion, the development is well along. We're actually building the flight hardware. Should significantly improve our knowledge on the lunar physics, gravitation and general relativity, and providing a fundamental selenidetic reference system, which I haven't mentioned. If you heard Brian Day's discussion, he's got 300 different maps. Unfortunately, those different maps don't know where they're set. And what you need is to both have a fundamental reference system and many tie points. And so therefore, we're pushing toward a number of corner reflectors in the future. And the restrictions we're talking about the measurements we're talking about put restrictions on the various theories of dark matter, dark energy, like the MOND, the modified Newtonian theories, and things like that. So, thank you.
All right, any gravity questions? Jack?
Doug, do you have an estimate of how many new corner cubes you would like to have on the near side experiment to, to improve measurements of the core, to do GR? What do you think you would really need to make major advances in those areas?
The lunar physics and the GR would be satisfied with 3 or 4 corner reflectors. The main reason for multiple corner reflectors is that general relativity talks about the center of mass. As I mentioned, the moon librates. And so we've got to determine the orientation of the moon, and that's the reason we needed 3 back in the Apollo days, and we would need 3 of the new ones. In order to tie down the selenitic coordinate system, there our classic example is that when LRO found Lunokhod 1 and told us, "Go, please measure it," we found that their coordinate system was in error by 100 meters. That's a big distance when you start saying in the north-south pole you're going to land on a mountain peak that's next to water. You would rather not land in the hole in the dark area where you don't have any light and you die. So tying that together is something where you could use many. We currently have 5. If we had 20, we would have a far greater coordinate system.
Oh, yeah, I was trying to speak to that issue. Is there a price point advantage if you buy or plan these for 10 or 20 as opposed to 2 or 3? One would think that this could become almost a standard piece of equipment for any significant lander. You would like to think that it would be that simple. Of course, it's not, but certainly the price point, would be a huge consideration in trying to convince people to get on board.
For additional units, the package you saw, the heart of that package is about 0.9 kilograms. You have an additional weight that has to do with how you fasten it to whatever's flying, the lander or the anchored unit. The price on that per unit after we get going would certainly be less than $1 million.
Then $1 million.
Less than $1 million.
So this shouldn't be a backbreaking thing.
Right. And yeah, I agree.
Okay, one last question.
How much are you dependent for the improvement that these could provide on being able to drill down? Because drilling a lot of considerable complexity and expense to the mission you fly on.
2 aspects of that. One is the 1 millimeter, which is what is the improvement by a factor of 50, is with no drilling. That's on a lander.
Okay.
To the drilling, I didn't do it here, but if I go back with a video Jack Schmidt gave me, they had horrible problems in drilling during Apollo. On the other hand, what Chris Zacny has done is to say, instead of twisting this or hammering it down, you blow air out the bottom and it blows the debris out. So instead of taking these little regolith pieces that link to each other and are very hard to push, you blow them out. And so we've done a test on that in which he turns it out, and I'm not going to drop this, but it just drops right in. And he has shown that works at 1/6 G in a vomit flight. He's shown it works in the vacuum and works with a JSC 1A simulant for doing the tests.
All right, thank you. Let's give our speaker another hand.